Okay, so now that we've gone over spring forces, we're gonna, as you can see from the title, we're gonna go over tension. So let me, before I begin, just make a list of all the forces that we have so far. So we have our spring force, which is just our spring stiffness, which is K times by delta X, which is our displacement, or you can just call that all that basically just Fs, you know. Then we also have our normal force, and then we also have a weight, and now we're going to have tension involved. So as you can see from this diagram right here, the basically the problem that we're going to be doing, there's no normal forces on it, just because they're not touching the ground and they're not like touching a wall or anything. They're not touching anything. They just have ropes connecting these blocks. So really, you're not going to have a spring force because there's no springs too, and you're not going to have a normal force like I just said. So it's just weight and tension that we're going to be dealing with for right here. So weight, which is just mg, you know. So I'll probably just be using this in the end. But anyways, so before I begin, I just want to talk about tension real quick. So basically, if we consider this rope right here, so we're going to say that the rope is massless, actually. So if the rope's massless, then ma is just 0 naturally, even if it's accelerating too. So static or dynamic, this is always true. So just if it's the mass is negligible, which it is for this case, just because the blocks are that much bigger. So later on, I might go over tension again in ropes, but just because the mass is also, it can be a function in the end. Like if you have a chain that's super heavy, but let's not focus on that right now. We're just going to say this guy is negligible. The mass is negligible. So anyway, so if we have our tension right here, we'll call that T, and we have basically the other tension down here, which will be S. So you're probably thinking to yourself, well, my teacher and probably all my other physics classes I've taken before, tension is constant throughout a rope. Well, that's true. So let me just show that real quick. So if we do the sum of the forces right here, we get T minus S. So T is heading in the positive direction, S is in the negative direction. Actually, that's the y direction. So really in the end, you get T equal to S. So really tension is just constant throughout any rope, whether it's moving or it's staying still. I mean, technically, there would be a mass associated with it, but it's so negligible to the blocks and almost any problem that you have that you're not going to be dealing with it at all. So I'm just pointing out tension is constant throughout a rope, and you'll see that's the case even with pulleys. It's a little bit different, but yeah, I'll talk about that more when I get there. So anyway, so let's just erase this right now. And I'll erase that. So just so I can write a T also. So T is that way, T is that way. So anyway, so now if we just start doing the free body diagrams of A, B, and C, we're going to have basically, so if we look at A, we're going to have basically T1 pointing up. So the tensions are going to be different throughout different ropes, but if it's the same rope, like we have right here, the tension is going to be the same. And that's always true. So we are going to have T1, and then we're going to have basically the weight associated with the block, and that's going to be MAG. And then we're going to have basically T2 pulling it down. So as you can see, I drew this force up just because it's going to be equal and opposite compared to the rope. So the rope's being pulled apart, so the rope is pulling the block up here and it's pulling the block down here. So anyways, so now if we move on to block B, it's basically the same thing again, except for it's going to be T2 on top, and then T3 is going to be on the bottom. And then we're going to have basically B, G as its weight. And then if we move on to C, there's only one tension now, so there's just T3 involved. So it's going to be T3 is going up. And then we're going to have M, C, G. So the key to these problems, if you get like a problem like this, is to start at the bottom. The bottom is going to be the easiest, you know. So as you can see, there's T1, T2, T2, T3. This one's just T3. So this one's going to be the easiest one to solve. So you can just solve for what T3 is right away. And typically you're going to be given these masses always. And G is just the gravitational constant. That's just constant wherever you're at on the surface of Earth. So if we do the sum of the forces of this real quick, so if we do the sum of the forces, so I'd write the y direction right here, but I'm just going to write c so that we know that we're talking about c real quick. So all this is going to be in the y direction. We're not dealing with the x direction at all. So, but anyway, so the sum of the forces on block C is just going to equal, so we have, oh, this is also pointing down. So we have basically 0 because it's a static problem. Oh yeah, by the way, static. And then we're going to have basically T3 minus mcg. So in the end, we know T3 equals mcg. As you can see now, I've actually given masses to each of these blocks. So I've said MA is got 1 kilogram, MB has got 3 kilograms, while MC is got, well, C's got 2 kilograms. So now now we can start plugging in hard numbers, because you're going to have hard numbers, well, not saying hard numbers, but actual numbers there instead of just symbols for your exams and homework. So now it's just going to be, really, if we want to know what T3 equals, really that's just going to be, so we have 2 basically times by 9.81, basically what G is for SI units. So we're going to get, in the end, 19.62, and that's going to be newtons in the end. So now if we move on, we're going to do B real quick. So the reason why we're going to be doing B is just because we know what T3 is now. We know it's equal to this. So I'm just going to implement this formula instead of implementing that number. A lot of students like to implement this, but I'm just going to have a lot more variables involved, you know. So we know what T3 is. We can actually solve what T2 is if we do the sum of the forces for B now, just because we're going to have one unknown and one equation developed from that. So anyway, so now that's going to be the sum of forces on B in the y direction. That's going to equal 0, of course, because it's static again. And then we're going to have T2 minus T3 minus MBG. So then T2 is then going to equal MBG plus T3, which is just, since T3 is just that, if we plug that in there, we can actually take out G from all that. So in the end, we just get MB plus MC, which is just the total mass of B and C, which kind of makes sense, you know. So as you go up, you should be getting more masses, and you'll see MA plus MB plus MC times by G is going to be T1 in the end. So yeah, so now anyways, is T2, if we use our calculator again, it's going to be 3 plus 2, and then times that by 9.81. So now we're going to have 49 point, what was that? 05 newtons for the tension in this rope. So yeah, as you can see, it keeps on getting greater than the one below it. So which makes sense, you know, because there's a mass below that one, you know. So, but anyways, so now if we do sum of the forces on A in the y direction, that's going to equal 0 again, which is going to equal, so now if we look at this, we have T1, and then we know what T2 is now. We know it's just this formula. So then it's going to be, so now we can solve for what T1 is. So if we started from A, B, and then if we did A, B, and C, if we did like the sum of the forces for all those in that order, then you would be a little bit, we'd be doing it backwards almost. But it's still fine. So if you're out of order, it's 100% fine. Really, in the end, you're just going to have to basically implement this one once you figure that and be like, oh, it goes into here, and then, oh, this one goes into here. So you're just going to be doing things a little bit backwards than doing it from the bottom to the top. So T1 is going to be in the positive direction for A, and then we have minus T2 minus MAG. So in the end, then we get T1 equals T2 plus, or I'll write MG first. So MAG plus T2. And then we know that T2 is just this in the end. So really we can pull out a G again, and then we're left with MA plus MB plus MC times by G, which makes sense, you know, if you had one giant block ABC right here, and you hung it by one rope, then you're going to get this, you know, so it makes sense in the end. It makes sense. So now we just need to figure out what this number is. So now really it's going to be 1 plus 3 plus 2, and then times that by 9.81, and we're going to get 58.86 newtons in the end. So as you can see, we're able to get the tension in this rope, which is just this, and then we're able to get the tension in 2, which is just this guy, and then we're able to get the tension in 1, which is just this guy. So dot right there. So yeah, so all you had to do is just do the sum of the forces for all the blocks. So if you have to, just try and do a lot of free body diagrams on your own, but in the end, you just got to break them up individually like this, and then just go from there. So